The main steam system in a power plant controls the flow of high-temperature, high-pressure steam as it moves from a boiler to a turbine and is used to drive a generator. To increase overall plant efficiency, some steam is extracted from the turbine and used to heat the feed water for the boiler. The rest of the steam is exhausted from the turbine to a main condenser. Condensate from the main condenser goes through the condensate system and becomes feed water that returns to the boiler through the feed water system. In this way, the condensate and feed water systems work together to supply water at the proper rate to support normal boiler operation. Because the functions of these two systems are interdependent, they're often considered one system, the condensate and feed water system. To maintain normal operation of a power plant's boiler, the water going into the boiler must be equal to the amount of steam that leaves the boiler and enters the main steam system. Keeping the boiler supplied with the proper amount of water is the job of the condensate and feed water system. This simplified illustration shows the arrangement or layout of some of the major components of a typical condensate and feed water system and a main steam system. Included are a boiler, a turbine, a main condenser, a feed water storage tank, and various pumps, heaters, valves, and piping. The area between the main condenser and the suction of this pump, the boiler feed pump, is the condensate side of the system. We'll look at it first. Additional systems are often connected to the basic condensate system that we've just seen. Typically, a chemical addition system is connected to the condensate system. In some cases, however, a chemical addition system may be connected to both the condensate side and the feed water side of the system, or just to the feed water side. In any case, the chemical addition system has equipment for adding chemicals that minimize corrosion and control the pH of the condensate or water. pH is a measure of how acid or alkaline the water is. Usually, a condensate system also has a makeup water system that is connected to the hot well. The makeup water system includes a condensate storage tank and purification equipment that is used to add pure water to the condensate system. The added water compensates for water losses that may occur during normal system operation or from leaks. Finally, various components in the condensate system are also equipped with instruments that measure pressures, temperatures, levels, and flows. These measurements are used in control loops that regulate operation of the system and give operators an indication of how the system is functioning. We've covered the condensate side of the condensate and feed water system. Next, we'll look at the feed water side. Now let's trace the flow of feed water through the system, starting with the boiler feed booster pumps. Not all feed water systems have boiler feed booster pumps, but in this case, there are 3 of them. These pumps increase the pressure of the feed water coming from the intermediate pressure heaters and send the water to the boiler feed pumps. In this example, there are 2 boiler feed pumps. They increase the feed water pressure further so it's high enough for the water to move through the downstream components. From the boiler feed pumps, the feed water enters a series or train of high-pressure feed water heaters. After passing through these heaters, the feed water is ready to go to the boiler. A feed water regulating valve controls the flow of feed water from the high-pressure heaters into the boiler's economizer. The economizer is the section of the boiler where combustion gases leaving the boiler are used to preheat the feed water that is entering the boiler. Finally, as with the condensate system, the feed water system also includes instruments for level, flow, temperature, and pressure indication and control. One more system that we need to look at is the extraction steam system, which serves both sides of the condensate and feed water system. Steam is extracted from the turbine and used as the heating fluid in heaters throughout the condensate and feed water system. Steam from the high-pressure section of the turbine is generally used in the high-pressure feed water heaters. Steam from the intermediate pressure section of the turbine is generally used in the intermediate pressure heaters and in the deaerator. Steam from the low-pressure section of the turbine is used in the low-pressure heaters. Heating the condensate and feed water with the steam from the different sections of the turbine increases overall plant efficiency. Although the examples that we've looked at are typical layouts, there are also many other ways that a condensate and feed water system can be arranged. You'll need to look at your plant's piping and instrumentation diagrams to check the exact layout of the system in your facility. Although the exact arrangement of components in a condensate and feed water system can vary, several pieces of equipment are common to most systems. In this part, we'll look at the major components of a typical condensate and feed water system. We'll begin with the hot well. The hot well is the bottom section of the main condenser. Condensate from the main condenser collects here and is then sent on through the condensate and feed water system, where the temperature and pressure of the condensate are gradually increased. Sight glasses indicate the level in the hot well. A level control loop is used to maintain the correct level of condensate. Maintaining the correct level in the hot well is critical for proper operation of the main condenser. Also, a low level in the hot well could cause the condensate pumps downstream to lose their prime and be damaged. A condensate and feed water system also has several condensers and heaters. Most of these are some type of shell and tube heat exchanger. For example, the initial warming of the condensate from the hot well is achieved by using the condensate as the cooling fluid in condensers. Gland steam condensers recover heat from the steam used in the plant's gland steam system. Air ejector condensers recover heat from the steam in the main condenser's air removal system. Both of these types of condensers are usually shell and tube heat exchangers. A shell and tube heat exchanger has a shell or casing with a bundle of tubes inside. The area that's within the shell and outside of the tubes is called the shell side of the heat exchanger. The area that's within the tubes is called the tube side of the heat exchanger. The heat exchangers that are used as condensers in the condensate and feed water system have condensate in the tube side and steam from the gland steam system or the air removal system in the shell side. During the heat exchange process, the steam is cooled and the condensate in the condensers is heated. U-tube shell and tube heat exchangers are used as heaters to heat the condensate and feed water that moves through the system. Condensate or feed water flows through the tube side of the heater, and extraction steam from the appropriate section of the turbine flows through the shell side. Because the steam doesn't come in contact with the condensate or feed water in the heater is called a closed heater. Some plants have parallel trains or strings of heaters, with several heaters in each train. All the heaters use extraction steam from the turbine to heat condensate or feed water. Typically, to recover the maximum amount of heat from the extraction steam, a train of heaters uses a cascading drain system. In each heater in the train, drips are subcooled by the transfer of heat to the feed water in the heater's drain cooler section. This helps keep the drips from flashing to steam in the drain line. The flow of drips moves from the highest pressure heater to the lower pressure heaters. That is, the drips flow through the normal drain line from one heater into the shell side of the next heater in the train. This heater has a lower temperature and a lower shell side pressure than the first heater has. The drips flash to steam because of the lower pressure within the heater's shell. The drips also mix with the extraction steam that's already in the shell. Thus, the drips are another source of heat to be transferred to the feed water in the tube side of the heater. In our example, the flashing and condensing process for the drips continues through the train of heaters until the drips from the heater that has the lowest shell temperature and pressure flow into the deaerator and become part of the feed water. In other cases, such as in the operation of low-pressure heaters, the drips from the heater with the lowest pressure and temperature flow into the main condenser. The deaerator heats condensate and also helps remove air and non-condensable gases that can cause corrosion. As this cutaway illustration shows, unlike a shell and tube heat exchanger, the deaerator is an open or direct contact heater. That is, condensate is heated when extraction steam and condensate contact each other and mix in the deaerator. As heat is transferred from the steam to the condensate, some of the steam condenses and some of the condensate is heated. This action strips or removes air and other non-condensable gases from the condensate. The heated and deaerated condensate that collects in the bottom of the heater is actually a mixture of condensate and drips from the heater. From the deaerator, the liquid will go to the hot surge tank for storage. From there, it will go on through the condensate and feed water system to the boiler. Air and non-condensable gases that are removed from the condensate flow out of the deaerator through a vent. The vent may vent directly to the atmosphere, or it may connect to the main condenser or to a vent condenser. The hot surge tank, which may also be called a feed water storage tank or a deaerator storage tank, receives the condensate from the bottom of the deaerator. The level of condensate or water in the tank supplies net positive suction head for pumps that have their suction piping connected to the tank. The correct net positive suction head is essential to keep the pumps from being damaged during operation. Also, the volume of water, called the surge volume, contained in the tank is used to meet changes in demand during operation of the condensate and feed water system. For example, if boiler demand increases, the boiler feed pumps begin pumping feed water from the storage tank at a rate that's greater than the rate at which condensate is being fed to the tank by the condensate system. The hot surge tank supplies enough feed water to meet the increased demand for the short time it takes for the condensate flow and the feed water flow to become equal again. Both deaerators and hot surge tanks often have additional connections. Examples are connections from the higher pressure feed water heater's cascading drain system and connections to the vent system from the high pressure heaters. Proper boiler operation requires the flow of feed water into the boiler to equal the flow of steam leaving the boiler. If too much feed water flows into the boiler, moisture could eventually build up and carry over into the main steam system. On the other hand, if there's not enough feed water flow to meet the demands of the boiler could boil dry. Feed water flow can be controlled in various ways. A feed water regulating valve may be used, or, as in this system, feed water flow can be controlled simply by varying the speed of the boiler feed water pumps. Other systems control feed water flow by using a combination of varying the speed of the boiler feed water pumps and changing the position of a feed water regulating valve. Two additional systems are normally associated with the condensate and feed water system. They are a chemical addition system and a make-up water system. The chemical addition system may be connected to the condensate system, the feed water system, or both. It generally includes pumps and associated equipment for adding chemicals such as hydrazine to prevent corrosion and ammonia to control pH. The make-up water system is connected to the main condenser's hot well. This system adds pure water to the condensate system to compensate for water losses that may occur due to condensate sampling or to steam or water leaks in the system. The make-up water is stored in a condensate storage tank. Make-up water system designs vary, but most also include purifying equipment such as evaporators and demineralizers. If you're responsible for keeping a condensate and feed water system running smoothly, you must be thoroughly familiar with normal operating conditions for the system so you can distinguish between usual and unusual conditions. Making regular checks of levels, temperatures, pressures, flows, and valve positions throughout the system as it operates helps you detect problems early so that major trouble and costly downtime can be prevented. Specific concerns associated with the operation of your facility's condensate and feed water system are usually covered in your plant's standard operating procedures and in the operating manuals for the individual pieces of equipment. In this part, however, we'll look at some basic operating checks that are common for most condensate and feed water systems. A typical condensate and feed water system includes several multi-stage centrifugal pumps. Checking the pressures, temperatures, and lubrication for the pumps during normal operation of the system is a routine operator responsibility. Checking pump suction and discharge pressures periodically helps ensure that each pump is operating correctly and that proper flow through the system is maintained. Proper bearing lubrication is critical to keep the pumps in a condensate and feed water system in good working order. To make sure that a pump's bearings are being properly lubricated, you should check for overheating, excessive vibration, contaminated lubricant, and low lubricant level. One way to check for overheating or excessive vibration is by touching the bearing housing. You can also use an instrument called a pyrometer to measure the temperature at the bearing housing, and a vibration meter to measure the amount of vibration. To check the flow, level, and condition of the lubricant, sight glasses are commonly used. If lubricating oil in a sight glass has an unusual color, this could be a sign that the oil has been contaminated and should be replaced. For this pump, a gauge measures the temperature of the lubricating oil leaving the pump's bearings. If the reading isn't within the normal temperature range, there's generally a problem that should be reported. Many pumps use cooling water to cool the pump's bearings. When you check these pumps, make sure that the valves in the cooling water lines are open. A centrifugal pump often uses seal water to help keep fluid from leaking out of the pump. During normal operation, you should check the seal water to be sure it's working properly. Also, if funnel drains are used for seal water leak-off, check the drains for proper seal water flow. If the flow is greater than normal, this could indicate a leaking seal. If a pump has a minimum flow requirement, a flow rate less than the minimum causes higher turbulence and greater friction, which generates heat in the pump. So recirculation lines and valves are used to maintain minimum flow and prevent overheating. If flow through the pump goes below the minimum flow requirement, the valves in the recirculation line are opened to maintain minimum flow. But when flow through the pump is above the minimum level, the valves in the recirculation line should be closed. Condensate pumps usually have suction and discharge vent lines that are connected to the main condenser. In most cases, the valve in the discharge vent line is closed after the condensate pump has been started and is operating normally. A low hot well level occurs when the amount of condensate leaving the main condenser is greater than the amount of steam that's condensing. This condition could cause the condensate pumps to lose their prime. A high hot well level occurs when the amount of steam condensed in the main condenser is greater than the amount of condensate removed by the condensate pumps. This condition could flood the lower sections of the tubes in the main condenser and reduce the condenser's overall condensing ability. In an extreme case, water from the main condenser could get up into the turbine and destroy its moving blades. A level control loop is used to maintain the correct level of condensate in the hot well. Basically, condensate flow out of the hot well is decreased if the level falls below a preset minimum, and increased if the level exceeds a preset maximum. A typical condensate and feed water system has several shell and tube heat exchangers or closed heaters. Some may be used as condensers, but most are used as low, intermediate, or high-pressure heaters for the condensate and feed water. The levels, temperatures, and pressures for all the closed heaters should be checked periodically during normal system operation to make sure that these operating variables remain within predetermined normal ranges. We'll look at some operating checks for a high-pressure closed feed water heater. Most of the checks for this type of heater also apply to low and intermediate pressure condensate or feed water heaters. To monitor the level in the shell side of the heater, you can usually check a sight glass on the heater. An abnormal level in the sight glass could indicate a problem that should be reported. Temperature gauges indicate the temperature of the feed water leaving the heater and the temperature of the extraction steam entering the heater. For proper system performance and the overall efficiency of the plant, it's very important that these temperatures stay within their normal operating ranges. Pressure gauges are used to monitor the pressure of the extraction steam that enters the heater and the feed water that passes through the heater. The reading for the extraction steam pressure normally varies with turbine load. The greater the turbine load, the higher the extraction steam pressure. Feed water heaters in many condensate and feed water systems are installed in trains or strings that are monitored as a unit during normal operation of the system. In this arrangement, the final feed water outlet temperature is commonly used as one way to monitor the performance of the heaters. The final feed water outlet temperature is the temperature of the feed water coming out of the highest pressure feed water heater on its way to the boiler's economizer. Checking this temperature is the quickest way to get an overall picture of how well the feed water heaters are doing their job. If the final feed water outlet temperature is at the expected level for the given load, then each of the feed water heaters in the train is probably transferring heat at the proper rate. But sometimes a heater within the train may be transferring heat at an improper rate, even though the final feed water outlet temperature is at the expected level. So periodically, you should also check the outlet temperature of each heater in the train. The deaerator, which is an open heater, and the hot surge or deaerator storage tank that's associated with the deaerator must also be monitored when a condensate and feed water system is in operation. Check the level of water in the hot surge tank. There's usually a level sight glass on the tank that's used for this purpose. If the level is too high, water could flow into the deaerator and, in extreme cases, even into the extraction system piping. If the level is too low, the net positive suction head for the pumps downstream of the tank is reduced. As a result, the pumps could be damaged. Monitoring the performance of the deaerator is important for maintaining overall system and plant efficiency. check the appropriate gauges for the proper extraction steam temperature and pressure. Look for any signs of leakage and make sure that all the valves for the deaerator are in the proper positions. Watch for excess venting from the deaerator. That can cause a major loss of heat energy and fluid from the deaerator, which will decrease plant efficiency. Also watch for insufficient venting. That will allow oxygen and other gases to remain in the condensate and feed water system and cause problems downstream. Problems can occur with any of the components in a condensate and feed water system, including the pumps, heaters, storage tanks, and their auxiliaries, such as valves, vents, motors, couplings, and piping. In this part, we'll look at typical examples of dealing with some operating problems that are common in most condensate and feed water systems. But keep in mind that you'll need to review your plant's standard operating procedures to learn the exact steps to follow in your facility. Many operating problems in a condensate and feed water system are relatively simple to correct. However, a problem in one component usually affects the operation of other components in the system as well. Consequently, some operating problems can require considerable troubleshooting skills. Several heaters are included in a condensate and feed water system, so heater problems are a typical operating concern. We'll look at some problems in a closed, high-pressure feed water heater. Improper venting of a heater can cause air binding. When this occurs, air is trapped in either the tube side or the shell side of the heater. Air that collects in the water boxes on the tube side of the heater can restrict the flow of water through some of the tubes. The restricted flow causes the velocity of the feed water to increase because the same amount of water must go through fewer tubes. The increased feed water velocity can cause the terminal temperature difference, or TTD, to increase, although the drain cooler approach, or DCA, remains normal. Another indication of air binding in the water boxes is an increase in the differential pressure, or delta P, across the heater. If air binding is indicated by either an increased TTD or an increased delta P, venting the air from the water boxes should return the feed water flow and pressure to normal. Air binding also occurs if air and gases collect on the shell side of the heater. The increasing volume of air blankets the tubes and prevents steam from contacting them. This, in turn, reduces the amount of heat transferred by the heater. As a result, the feed water outlet temperature decreases. The TTD, however, increases because the extraction steam temperature remains the same, even though the feed water outlet temperature has gone down. The efficiency of the drain cooler isn't affected, so the DCA remains normal. You can usually correct the problem of air binding on the shell side of a heater by venting the shell side to remove the air. The TTD should then return to normal. As a result of the restricted heat transfer caused by a high heater level, the TTD increases. The DCA, however, usually remains normal because the flow of drips through the drain cooler may not change, or it may be less than normal. To determine whether an increased TTD is caused by air binding or by a high level, check the sight glass for the shell side of the heater. If the level in the sight glass is high, then the problem is most likely caused by an abnormal level, not by air binding. If a heater's level is too low, steam is able to blow through the heater and out the drain. In turn, the flow of extraction steam increases, and this can cause erosion inside the heater and eventually tube failure. Because the low level allows steam to flow through the heater's drain cooler without condensing, a low level causes the DCA to increase drastically, while the TTD typically remains at or near normal. Tube leaks are another common operating problem associated with closed heaters like this high-pressure feedwater heater. Even small leaks can significantly increase the volume of water in the drips, causing the lower tubes in the heater to be blanketed with feedwater. Tube leaks also make the heater's level control valve open farther than normal. As a tube leak becomes larger, the volume of water flowing into the shell side of the heater can exceed the level control valve's capacity. Then the emergency drain valve must be used to control the level in the heater. A large tube leak is a serious problem that calls for immediate attention because it can allow water to enter the turbine. To prevent damaging or destroying the turbine, you should isolate and bypass the heater as soon as possible. Of course, operating with even a relatively small tube leak is inefficient, so it's important to find small leaks early and get them corrected. Small tube leaks may be difficult to detect, though, because they don't show up on instrumentation. But some small leaks may become noticeable when you calculate the TTD and the DCA for a heater. In many cases, operators must determine exactly which heater in a train is not operating properly. In this example, one heater in a train of high-pressure feedwater heaters is malfunctioning. As a result, there's an increase in the temperature difference, or delta T, across the higher pressure heaters downstream from the malfunctioning one. The increased delta T causes more heat to be transferred in the downstream heaters, making up some of the difference caused by the heater that's not operating properly. To locate the heater that's not operating properly, you should generally start by checking the final feedwater outlet temperature to see if that value is within the normal range. Then work backwards, noting the heater outlet temperature for each heater in the train. If the difference between the actual reading and the expected one becomes greater with each heater, there's a malfunctioning heater upstream. To pinpoint the exact heater that's causing the problem, follow a step-by-step troubleshooting procedure, which includes checking the temperature rise across each heater, calculating their TTDs and DCAs, and checking the positions of their normal drain valves. Then comparing the actual conditions with the expected normal conditions for the heaters at the given load. A typical condensate and feedwater system also has several pumps, so operating problems often involve troubleshooting pump malfunctions. For example, this operator notices that although this boiler feed pump is operating at top speed, the flow of feed water to the boiler is inadequate. To keep the situation from getting worse, a second boiler feed pump is brought online. This increases the feed water flow to an adequate rate to keep the boiler operating properly. Then company procedures are followed to analyze and correct the problem. Detailed troubleshooting could determine that the inadequate feed water flow was caused by an operating problem in the first boiler feed pump. On the other hand, further analysis could show that the pump is working properly, and a malfunction elsewhere in the condensate and feedwater system could be the cause of the inadequate feed water flow.